Good morning and welcome to Chemistry in the AM. Joel Sandelka. We're going to record this lesson and we're going to review what we did last week for two reasons. So that we have a recording of the first, second, third lessons or whatever that we did, the activities, and just because we actually will be handling chemicals, I want to review this. First day for our atoms and element unit, we went over a few things. I showed you around the lab, the shower, and the eye wash station, etc. The main things after I played around with acid, water, and stuff, is sometimes you can't tell the difference what's in a beaker. I showed you right away. I played with that sulfuric acid that looked very similar to the water. One just wet the paper towel, the other ate through it immediately, right? So, follow directions. Do not do unauthorized experiments. If I have something sitting around that's not labeled, ask me to label it and stuff like this if you're supposed to use them. If you're uncertain what the chemical is, because there's a big difference. Wear glasses when asked, and I'll only ask you to when it's dangerous. No horseplay, no fooling around. Follow directions. That being said, what did we do? Well, we mixed sugar, which you would actually, most people would not think that sugar would actually react the way it did with acid, right? Sugar is a household item. I wouldn't even call it a chemical, like, somehow if it's everyday use, you don't think of it as a chemical. Anyways, but it's got a ton of energy when the bonds are broken, and they are when it's added to that particular acid. We took it outside because it's slow to start, so you might even mix them and not think. Remember how it took about 2 minutes or so? It was really slow to start. You might not even think there's anything wrong with it and just leave it, turn your back on it. 2 minutes later, it starts reacting. And that's about what happened, right? We had the question, is this chemical or physical change? It definitely was a chemical change, right? Why? The kind of evidence you saw is that there was definitely, after a little while, there was a color change. There was definitely heat, energy involved, right? It got extremely hot, you could tell, and I wouldn't let you touch it to tell. Bubbling, which meant a gas was being released. Something new was created, a chemical that wasn't there before. That's the main thing with chemical change. We'll talk more about that. It was really dangerous, actually, and I did it outside on the parking lot because that particular time it dripped over too, and I actually had to clean it up with, to neutralize the acid, I used baking soda on the ground and then scooped it up and moved it and stuff. Anyways, so it was definitely a chemical change, and from things that you like, something like sugar, something you wouldn't even expect probably to react like that. And I then later mentioned when sugars of different types are the basis of a lot of the high energy foods, carbohydrates that you eat, right? And that same kind of reaction goes on in your stomach and in your intestines, but because of enzymes at a much lower temperature. But you can see why you get a ton of energy from sugar. You saw it released. That's a lot of energy. That was one day, then the next. Pardon me. We had a brief look over for safety reasons. This is more actually common knowledge, like household safety, stuff like this. Warning symbols. You often see the symbols inside a triangle, diamond, or an octagon. The stop sign, the octagon, is really be careful. The other ones are like, yeah, be careful. And the four common ones from household chemicals that we see, we said corrosive. Basically, think about that hand, skeleton, X-ray of your hand. It could eat through skin. That acid, for example, could eat through skin. I don't think if you dipped your hand in that acid, you'd come out with a skeleton. Doctor don't want to try it. But it would irritate your skin. You'd have to wash your hands immediately. Get your hands underwater if you smell something. I'm not going to give you that kind of acid, actually, at that concentration. Anyways, but at home and stuff like this, wash your hands immediately and then check into it. Follow up. Flammable. The word inflammable is a synonym to flammable. I just want to bring that to your attention. Don't think it's not flammable. Inflammable means flammable. It can burn. poisons, toxic. Obviously, that there's a danger of ingestion. And then finally, explosions, right? A lot of aerosol cans. Be aware of these things, right? Okay. So, take a look at that. Then we just started on what we're continuing with today, organizing matter. Okay. What happened to my pictures? I'll be darned. You guys remember there was pictures here, right? I'm not crazy or something. I'll have to play around with that. I've been no, I can't. That was what the pictures look like, but I have to flip to the other one and just put, I'm gonna pause the video here. Okay, back to this. I fixed a little bit of most of these physical changes you are aware of. Melting, freezing, evaporation, condensation. You might not have said too much, but you're aware of it. Gas to liquid. You see the sweat on a cold drink on a humid day. Depositing, deposition is solid to gas. We said the example would be frost on a windshield. Might have been today, this morning. Sublimation, a solid going straight into gas. Somehow, ice cubes shrink in your freezer without going into liquid state. That's an example, right? We talked about that. Those are all physical change. Why? When we say the word water commonly, we're actually thinking liquid water. You say steam for the gas form, and you say ice. But they're all water molecules. So it's actually the same substance, three different forms. I use water because it's common. You are aware of those three phases. Anyways, the physical change, you actually don't change the substance. You might change its appearance. And I want you to jot that down because that's where we're going to go. Okay, I used to have a picture there. I don't know what happened to the software. Like screwed up. So, no new substances. One thing that is emphasized often in elementary school is physical changes can be reversed. I'm not going to say easily reversed. It involves energy, and there's some chemical reactions that are just as easily or more easily reversed than some physical changes. Freezing and melting, you're totally aware of an ice cube melting, and then you can refreeze it, stuff, right? Okay, so reversible. I'm not going to say easily reversed because cutting into pieces. Well, how about this sheet of paper here? Is this easily reversed? I'm ripping it so far until I can't rip it. No, it's not easily reversed, right? So physical change isn't necessarily easily reversed. Like, you could take all these fibers and recreate a sheet of paper, but it won't have the same printing. It can be reversed, but it requires a lot of effort. Anyways, so is a broken heart chemical change or physical change? Can you reverse that? Think about that. Just kidding. Anyways, well, why do things do what they do? Well, these particles, we talked about solid, liquid, and gas particles, right, closer together and stuff like this. We're going to use water because it's the most common liquid. It's dirt cheap, and food coloring. And I'm going to show you this, and I'm talking about something that I realize the screen is frozen. Particles are in motion. I'm going to just show this. I'm going to pause this. I'm going to drop food coloring in and not stir. We filled our beaker with water. We know that the molecules in the water can vibrate, just a little back and forth motion like you sitting and wiggling in your seat. But then the molecules themselves can travel left, right, up, down. We call that translation motion, but there's just that linear kind of left, right one could go on a curve. Just like you walking around calmly around the classroom. Plus the little molecules inside there can do like somersaults, rotational motion. Just like if I asked you to clear out the chairs, you could do somersaults, cartwheels, and stuff like that. So you've got three types of motion. The left, right, kind of translational motion, the rotational motion, plus the vibration while you're doing it, okay? If I drop in food coloring, now the water's no longer swirling. And I don't stir it. If I stir it, there's a reason why I can't. Now, coloring in one spot, and it's slowly, kind of looks neat. I don't know if you can all see it, but you've seen it before. Why is it moving around? It would have been better if I filled the beaker up over the weekend. I only let it sit for 3 or 4 minutes. So a bit of that is because there's still a slight swirl from filling the beaker. But it's not really like, it's not like being stirred, right? Why is it spreading around then, just from what we explained? Okay, sure. Yeah, like the particles are ping-ponging back and forth and colliding with the colored particles, right? Without even stirring, in about 2 or 3 minutes, that'll be spread out fairly uniformly, right? Okay. So, and you've seen this kind of thing before, right? That's all I want. You didn't have to draw anything. Just to get us thinking about the molecular motion. Because molecular motion is all about physical change and chemical change. I used to have images here. We're going to play around with chemical change while that just sits. Can you jot this down while we... And my images disappeared for some reason on the software. One or more substances are formed in chemical change. The substances have different properties than those of the starter. Examples: cooking an egg, adding icing to sugar, burning gasoline. I'm going to tell you something. Chemical change sometimes isn't easily reversed, but it is very reversible. And we'll talk about what kind of chemical change is easily reversible, or easily, but is reversible. As demonstrated, we're going to just jot one more thing down. Many chemical reactions are reversible. I want that down just in case somebody had it in their head that it wasn't the case. Some aren't. Cooking an egg, good luck trying to undo it and get back into a yolk, right? And while you're jotting that down, I'm going to remind you that we talked about this one in your electricity unit. There's a chemical reaction every day most people who own a phone use, and they reverse it every night, whenever. Sometimes when they come in this classroom. How does your phone get energy? Like what kind of battery kind of thing? What's happening? There's a chemical reaction. There's a battery that's, the chemical reaction is transformed into electrical energy, right? And it goes one direction, that gives off energy. And then when you plug it in, the energy from the outlet is transferred into that battery and reversing it, right? And then storing chemical in that battery, right? So you definitely have experience with reverse reactions. You don't think about it, see it. Now, here's what we're going to do right now. Jot something down. Physical change, chemical change. We're going to make a very basic one here. I'm going to get you to jot this down. Oh, I got the observations already. I'm going to pause this so if you're watching the video, jot that down. It's cloudy at first. The baking soda dissolved in the water, okay? I want to jot that down. Now, I'll swirl it around. Is there gas in the cookie? Well, we didn't see any evidence of gas. Okay. Let's see what I mean. Now, baking soda and vinegar. You guys already know what's going to happen with baking soda, right? Bubbles, which indicate a gas. I'm going to just trap some of that gas inside. There's no crazy energy or stuff like this involved with this, but we definitely see it foaming up, which means a lot of gas is being, right? There's something new being created. A new substance is created, that means chemical change goes on. Let's see though, do we have any other evidence other than you taking my word for it? Let's take a scoop of that gas and see what happens. Here's the way previous year's students described it. It foamed up, bubbled up, which means a gas was formed, and I let you know that it's CO2. And then we were able to scoop up the gas in the beaker and pour it onto a flame, and it would extinguish the flame, right? So we saw definite evidence that a new substance was created. That's chemical change, right? Chemical change. And it smells like a cake, birthday cake or something. Here, just blow out the candles, right? Okay. So jot that down. Your notebooks. We're going to get ready for a lab tomorrow. And you put, and I have the handout for you. You don't have this textbook. It's an old textbook. Lab, page 24-5, science directions. Physical and chemical change. I gave it as a study question. That means we are going to form a purpose. And we aren't going to rewrite the procedure. Actually, that's too much. We got to get to the purpose before you get to it. So if we're trying to ask this question, science, we state it just as a purpose, a non-question. And we know a phrase we can add to any question that works for most. Make a purpose. We practice this in electricity. What is a good purpose in this case? Yes. Great. So simplistically in grade 9, we can make most purposes by asking a question and then just putting the phrase to find out or to determine. Good, thank you. Don't put today's date on there, because we'll see. You don't know who your partner is until tomorrow. Start with your name, though. I don't want that. So, purpose. To determine. Like, which of the 4 chemical changes Okay. So that's why I pause this so you leave the right amount of space. And then just jot this down and I'm going to have this. Oh, maybe it won't. It's frozen here, and it is. Oh, spin. Sure ain't working good today. I'll pause the video.